Today we will finish our module on tests, and we will also start talking again about model fitting. About tests, we have seen the general method for building tests, which is based on likelihood ratio statistics. But there are a number of other tests, in fact a huge variety of tests that have been created, and I will show to you some of the ones that are commonly used. So back to the problem we had of testing whether a data set comes from a given distribution, for example, Gaussian. We have seen a goodness of fit test that consists in discretizing the distribution values and doing a test about the number of objects in every bin. There is a radically different approach, which consists in comparing directly the CDF. So I have some data that I assume IID. Invariably, all tests assume that the data that you have is IID. So if it's not, then you'll have a problem, or you may need to filter the data or model them in some way to consider the residuals that then may be IID. So I assume I have a data set that comes from an IID factory, and I want to test whether it comes from a specific distribution, which I write capital F here. Capital F here stands for the CDF of the distribution. And the null hypothesis is this one. The general hypothesis is the world of distributions, all possible such functions, which are all increasing functions that take values between 0 and 1. And the idea is to compare the empirical distribution function to the theoretical one. What is the empirical distribution function? Well, it is given here. That's the one we have when we ask MATLAB to plot CDF from a data set. So we'll have a small staircase function. If the number of points is very large, it doesn't look like a staircase, but it's a discontinuous function that has a jump of 1 at every point where there is a value, and a jump of k if at some value xi there are k data points here. So that is the empirical distribution function. And the idea of this test is to look at the L1 norm of the difference between the theoretical function and the empirical one here. This can be computed because in practice, the left is a continuous function most of the time. The right is a discontinuous function that increases by steps and is constant between steps. So in fact, to evaluate this quantity, you need to compute the value at the steps of this function here. So it's something that's fairly easy to compute numerically. It has a complexity which is order n, where n is the number of data points here. Of course, that works if we're able to say something to create a pivot from that. And it turns out that this quantity here is, in fact, a pivot. In other words, this quantity, capital T, so T, remember, is the quantity we obtain out of the data. But in the context of tests, we consider it as a random quantity if we consider that our data is random. So if the data set that we have is truly random, then the f hat itself is a random function. So that is a random quantity. Out of the f hat, we distill a single number. So t is a real valued random variable. The distribution of f happens to be independent, the distribution of t happens to be independent of which function f we're testing against here. And the rejection region, rejection means we reject h0, will be, of course, when this is large. Of course, f is never exactly equal to f hat, but if the data comes from f, then f hat should be close to f. That's the law of large numbers that said that the empirical function tends to the theoretical function when the number of data points gets large here. The fact that it's a pivot is something that looks strange, but if you remember tricks we used, it is not so surprising. The trick is simply to consider that if I apply a CDF to a sample of the random variable that is produced from a simulator from the same CDF, we obtain a random variable that is uniformly distributed. That's a trick we've used, for example, when we use the CDF inversion method for sampling data. By inverting capital F, generating capital U, we obtain sample of X. That's the CDF inversion formula. So here the idea is based on that. If F is continuous and strictly increasing, at least over some interval of interest, then we will do a rescaling. Instead of studying the capital X, we study the capital F. Since we're testing against capital F is well known. And then it's easy to see that this rescaling translates into another rescaling of the empirical function. So f hat, the empirical CDF of my data, can be rewritten as the empirical CDF applied to f of x here. The empirical CDF of G, where G is the empirical CDF of the rescale data. Now, what is the empirical CDF of rescale data? Is the empirical distribution of n data points that come from a uniform distribution. Now, this is not a very nice thing. There is no closed form formula to express capital G hat with a simple, the distribution of G hat is not easy to write. But if I compute this thing here, which is exactly through this rescaling, is exactly the same as the metric we used in the test before, we see that the statistic of the test can be expressed as this quantity, which is what? Is a supremum over all the values of u, where u is a non-random number between 0 and 1, of g hat of u. G hat is a random function, but the distribution of it is, at least in theory, well known. So it's the distance, the L1 distance from this to the first diagonal, which corresponds to the CDF of the uniform distribution. So capital T is, of course, a random variable that has a well-known definition. It's not so easy to obtain. We could obtain it, for example, by Monte Carlo simulation, but it is obtained by other more sophisticated tricks. So all statistical software packages have the distribution of T. And for large n, tail is known also exactly. So it decays according to the rule that is given here. So it's approximately an exponential decay for the tail here. So that means that in practice, not with a very nice closed form, but in practice, we can compute the p-value of this test, which is called the Kolmogorov-Smirnov test here. I did it for the sample we had before. Remember, we had the file transfer times that in natural scale obviously did not look Gaussian, and in log scale perhaps looked Gaussian, and this is where we're interested in performing a test. Here I cheated a bit because Kolmogorov-Smirnov tests whether the data comes from one specific distribution. So I had to rescale the distribution by its standard mean and estimate its standard deviation. And by doing that, I know that the p-value will be overestimated. That's a discussion we had last week already. So I did this with this little cheating, and this is the p-value I obtained for the diagram on the left. We know it's not Gaussian, so we expect the p-value to be large, and we find 1. Not so exciting because we knew already the answer. Here the question is, statistically, does it look Gaussian? And the answer here is, the p-value is 0, which means, of course, we reject the Gaussian assumption here, but this we knew already. For the transform data, we obtain a p-value which is around 30%, which is for statistics large. That means we accept the fact that it's Gaussian, and so this random deviation at the beginning and at the end are perhaps not large enough to reject. In fact, I don't like the idea of having to estimate here and obtaining a p-value that's overestimated. Statisticians tell us that this overestimation is not large if the number of data points is large. So probably, given my p-value is large, this overestimation does not hurt. There is a variant of Kolmogorov-Smirnov, which is called Lilly-Force, that does an empirical correction. So that reduces a bit the p-value and will be more correct. But explaining it in detail would take too long. So that's an example of tests which I would say are the state-of-the-art tests today to test whether data comes from a given distribution, Kolmogorov-Smirnov or the Lilly-Force variant. Here is a variant of tests we saw that were called ANOVA, when I tested whether one compiler option would have a significant effect, or whether the randomness I seen can be explained simply by the randomness of the data. I assumed the data was coming from a Gaussian distribution, and I performed a test using likelihood ratio framework that gave what is also called an ANOVA test, because the p-value can be computed simply from the residual mean square errors. If we can avoid using the Gaussian assumption, it's better, because the Gaussian assumption may be true. Often it is not. Often it requires rescaling to appear to be true. So there are other tests, and one of them is based on median here, which is not surprising. We have seen that when we wanted to compute confidence intervals, if we want to compute confidence intervals for the mean, we needed somehow a Gaussian assumption, at least for the aggregation of many data points. So we need that the n is large and the central limit theorem holds. But if we wanted to avoid this, we could look at the median. So we find the same dichotomy of families of tests here. So there is the so-called median test that applied to paired data, for example, to test whether the difference between type 0 and type 1 is significant. I can apply this test by looking at, is it true that the median is 0 or not? Instead of the mean, by taking the median, we are more robust to distributional assumption here. Well, that's a trivial test, because we have seen that whenever we want to test things of this nature, it is sufficient to compute a confidence interval for the median and reject H0 if 0 does not belong to the interval here. So that still has a name. It's called the median test. We would not need the theory of tests for that, because we have seen that testing one parameter of a distribution is equivalent to computing a confidence interval for this parameter. But it has a name. So here I've applied it to my data set here, where obviously here there is a significant difference, and the median test gives me, the confidence interval gives me an interval that does not contain 0. So I reject I say that there is a significant difference. I reject H0. The interest of this is when we can do similar things, but for non-paired data. When we want, for example, to compare a data sequence X to a data sequence Y, they are non-paired, so we cannot simply take the difference X minus Y. And for example, also the number of data points in the two sets don't need to be the same. But we will still like to see whether there's a significant difference between the two. So the so-called Wilcoxon-Ranson test assumes that the distribution is common, possibly by a location shift. We'll talk about location shifts and rescaling in a few minutes. Location shifts mean they have the same variance, essentially, but they don't have the same mean. But since we're not talking here of distributions that have a variance, possibly they could have infinite variance, we talk of location shift. But mentally speaking, that's what it means. So it's very similar to the ANOVA test, but we're not making the assumption that they are Gaussian, but still we're making the assumption that in some sense, the variability of the two data sets is the same, right? Because if Y, for example, is much more variable than X, then the variance of Y would be larger, and then we won't fit in this story here. So if this is acceptable, the Wilcoxon-Ranson statistic is this thing here. We take the two data samples, X and Y, and we put them together in one, we concatenate them, and we sort. So if all the X's are much smaller than all the Y's, when we sort them in this big bag, all the X's, or many X's, will be at the beginning, and many Y's will be at the end. So that's the idea. So the idea is to take as statistics R the sum of the ranks of X in these concatenated things. If the average rank is N1 plus N2 over 2, right? If X is much smaller than Y, then the average, or the sum of the ranks of X So if I take not the sum but the average divided by n1, r divided by n1 would be much less than n1 plus n2 over 2. So this means that we have, at least intuitively, a way to decide whether x is much smaller than y without needing to do any specific assumption on the distributions here. So this quantity here is also a pivot. And furthermore, when the number of data points is large, it is approximately normal with a mean that is given by this and a variance that is given by that, so that the p-value can be obtained, at least for n1 and 2 large, by this simple formula. So that's a very commonly used test that does not require the Gaussian assumption. I did it on the 3 samples that we studied already last week with ANOVA tests here, and we find quasi the same p-values as with ANOVA, which is not surprising because in this case the distributions are Gaussian, so we expect the 2 results to be essentially before testing the same thing. In particular here, the test, if you recall, say that the parameter set 3 has a large p-value, which means we accept H0. We think that they come from the same distribution, whereas for the other 2, we don't here. And the ambiguous case was set 2, and the tests here, whether we do Wilcoxon rank sum or ANOVA, will give the same. Wilcoxon rank sum is for 2 samples. If we have more than 2, we have quasi the same thing, but it has a different name. It's called the Kruskal-Wallis. So Kruskal-Wallis will do a similar, a bit more complicated to express, but similar test by comparing the ranks of the samples, and will give a result that is whether all the samples, all the 1, 2, 3, 4 samples come from the same distribution or not. Last, I will conclude with this test that is an alternative to testing whether time series that we have is IID. Here, the idea is, so we've seen that one way to do it is to do an autocorrelation plot and test whether the autocorrelation coefficients are within the error bounds here. Here, another idea that's radically different consists in comparing what is called the turning points. So we see that all those tests are using simply comparisons that are qualitative to be independent of the scale and therefore of the distribution. The idea is that if I compare 3 consecutive values of my data sequence, right, you can have those 6 possible orderings. It may be that the first one is the largest, the second largest is the middle, and the third one is the smallest. And you can have all the different orders that are explained on those schematic diagrams here. And it is not absolutely obvious, but still intuitively acceptable that if the data is IID, that means if x1, x2, x3, or xi minus 1, xi plus 1 are IID, remember IID means when we draw xi, we forget any information we had that led to drawing xi minus 1, any information other than the distribution here. So if there is truly independence, there is no reason that any of those cases would occur more than the others, because all the possible permutations have the same distribution. So which is in fact exchangeability, but if the data sequence is IID, it is exchangeable. So under the null hypothesis, the 6 cases are equally probable. And then the turning point test counts what is called a turning point. A turning point is when we are not in the first or the 6th case. The 6th case, we have a given ordering of the 3 data points. Here we have another ordering. And in all the other cases, the ordering changes. So we have a turning point in the middle here in those 3 cases. So the probability that there is a turning point when you take 3 consecutive values under H0 should be 2 out of 3, 4 out of 6 here. This gives, now of course there is some, if you look at all the possible turning points, there is dependencies between them, because if I look at 3 data points and then for the next sample I will use xi, xi plus 1, xi plus 2, of course I will reuse the same data, so there's a dependency, so the computation is not entirely obvious, but it can be done. And for large N, again, it is approximately Gaussian. It's a variant of the binomial distribution for the standard case, for the exact case. And for large N, it's approximately Gaussian with a mean that's given here and a variance that's given there. Therefore, similarly to what we saw before, if the pivot has if the statistic has a Gaussian distribution with a well-known distribution, that does not depend on the distribution of X, but only on the number of data points, little m here, then we can test whether H0 is acceptable or not. Voila, that's all we will see for tests. The more, not all, we will see other tests in other contexts, but of course, whenever you're able to analyze something of the data, you can test whether what you're seeing in the data is compatible, consistent with the hypothesis you're doing. And I've cited here the very widely used tests that have the the important property that they're independent of the distribution. So to conclude, what did we see about tests? Tests are useful to quantify whether a difference is statistically significant or not, but typically we use it when the difference is small. If the difference is large, you compute the quantities of interest, your metrics with confidence intervals. If the confidence intervals are very far apart, you don't need to bother doing a test. But if it's not clear, or you're not just measuring one parameter of a distribution, but a more complicated assumption, then a test may be useful. We've seen that the size of a test, which is in the literature almost invariably 5%, but in reality, it should suit the resolution of the data. So it may be worth computing the power if you have a very important case to study. Like for confidence intervals and anything we're doing in statistics, there are probably assumptions in the model that may need discussion. And as we have said a minute ago, confidence intervals typically give much more information than tests, so it should be preferred. So you should think twice whether you need a test or not. There is a dispute in the scientific world whether tests are good or not. I don't have personal opinion about that, but I invite you to read, for example, this recent article in the Journal of the Swiss National Science Foundation, for which I give the link in the lecture notes, where you can see the opinions of 2 statisticians, one who says, yes, tests are very useful, the other says tests are not useful. Much of the dispute comes from not having had a serious class, like I hope this one is, about tests, and not always understanding what a test is really doing. So a test is testing with a given size, most of the time ignoring the power. So it's not necessarily saying that with 95% probability, my result is certain. The story is a bit more subtle, right? The size of a test says, among all the possible data samples that the world or God or nature could generate, the probability that we do a misclassification when the null hypothesis is true is less than 5%. That's what it means. But in reality, I have only one data sample. So this interpretation should not be stretched too far. And that's probably what's at the heart of the dispute that you can read here. Voila. We end here the story about tests. And without further transition, we will revisit a number of important topics on model fitting that are left to a second module so that we could advance the labs quickly. And also because now that we are used to the statistical method, we are perhaps more able to appreciate a number of supplementary aspects. The first topic I will discuss now is features of a distribution. So what do I mean by that? Well, very often when we have to do statistical modeling, for tests, for example, or simply to create a simulator, we have to choose a distribution. For example, if you simulate a charging station and we want to simulate the arrival of cars to a charging station, perhaps we'll use a Poisson process for modeling the arrival of cars. By doing that, we've chosen a distribution. That's the distribution of the interval of times between arrivals here. Why did we choose this distribution and not another one? Being able to do so is very important because it allows us to create simulators that are way more powerful than simulators that are just trace-based. If we can capture the arrival of packets in a network or of cars at a charging station by a model rather than having to use traces, then we can do much more powerful simulation studies. Of course, we cannot claim that we have measured things on a real system, but we're able, for example, to project ourselves in the future and do things like saying what would happen if the intensity would be multiplied by a factor 10 or 100, something that trace-based simulation has a hard time producing. In order to be able to choose a correct distribution, we need to have a catalog of distributions in our head, or at least in our software. And we need to know a few things and avoid a few traps about choosing distributions here. So distributions have attributes: shape, kurtosis, skewness, power laws, and hazard rate. Those are attributes that you can test on your data and that are typically useful for us to choose a given distribution. So we will discuss about those attributes now. What is the shape? Well, the shape is what you see when you plot the PDF. For example, the shape of a Gaussian distribution is a bell. It's called the bell-shaped distribution. Abstractly, the shape is what remains when we remove equivalence. So we say that two distributions, here I equate distributions of real valued random variables with their PDFs. That's a one-to-one mapping, so it's more convenient to talk of the PDFs. And I say that two PDF have the same shape if they differ by a linear, or more precisely, affine change of variables. So the second PDF differs from the first by rescaling in a linear way, multiplying by S plus shifting by M. And here I impose S positive because S negative would mean a symmetry in some sense. So I assume S positive, and this change simply means that I've done a change of location. M means I shift the origin of the x-axis, and S means I change the scale on the y-axis. It can be seen that this is the same as saying that if I interpret f as the distribution of random variable x and g of a random variable y, then there's a relation of this type, a linear change of variable for the random variable. Here's the proof in case you need more confidence about this, but I'll leave you to study that. So two distributions that differ only by a location shift and a change of scale on the y-axis are giving the same shape. In fact, well, that's the definition of a shape, but the idea is if I ask MATLAB to plot a PDF, for example, an empirical PDF for a large data set, so if I see a smooth function, MATLAB will automatically choose the box for the x and the y-axis. So two distributions that differ by a location shift and a scale parameter will give exactly the same MATLAB drawing. Perhaps if you read carefully the legend, they will be a bit different, but the drawings will be the same. So the shape is what remains when we ask the drawing software to automatically choose the axis system here. Here are three different distributions. I call them N for normal or Gaussian. N01 is the standard Gaussian distribution. It's called standard because the mean is 0 and the variance is 1. Then the generic Gaussian distribution. And here a specific Gaussian distribution with variance 0 and mean mu. Which of these distributions have the same shape? I close the poll in a few seconds. We see that we have a large variance. Let's see what is the correct answer. Well, the standard Gaussian and an arbitrary Gaussian distribution have the same shape, at least when the sigma is non-zero. Because we know from the classic formula that the Gaussian distribution with mean mu and standard deviation sigma is the distribution of sigma x plus mu, where x is a standard Gaussian distribution. So that is true, except of course the sigma must be non-zero. If C is zero, we have something that looks complicated, but in reality very simple. A Gaussian distribution with standard deviation 0 means the random variable is constant. With 100% probability, the value of the variable is mu, for example, here -6 here. Which means that the PDF does not exist, at least not as a standard function. It exists like a Dirac distribution, or some people call it Dirac function, which we typically draw with an arrow, means it goes to infinity, but the integral of this is finite, is 1. So this does not have the same shape. There is no way you can stretch or rescale that this arrow gives this nice bell shape here. So apart from this little trick, the take-home message is, yes, all Gaussian distributions are in fact the same, with the exception, of course, of the Dirac distribution. When you look up a catalog of distribution, and probably the best catalog today is Wikipedia online, you will see many parameters. And the vocation of Wikipedia is to give all the possible details you need to know. So Wikipedia will give you all the parameters. But when you want to pick a distribution here, of course, the shape and scale parameters, so all the parameters that affect the shape, so the scale and location, sorry, should be removed because they are in fact same distribution, just placed differently on the axis system here. So it's important to find out, and Wikipedia gives it, typically tell you this is a shape parameter or not, or this is a location parameter or not here. For example, the Gaussian distribution with parameter mu and sigma square has mu and sigma as scale and location parameters, which means you can ignore them. You can simply take n0, 1, and you have all the Gaussian distributions here. We've encountered several times the exponential distribution. So the exponential distribution is the one with PDF exponential minus lambda x times a normalizing constant, which is just lambda. And we've seen that it is at the heart of the Laplace distribution. When we symmetrize it, we obtain the Laplace distribution, which has positive or negative values. The exponential distribution takes only positive values. And the exponential distribution is used in L1 estimation, for example, to model noise that has larger tail than standard Gaussian noise. It's also used to model the memoryless property. We know, for example, if we wait for the arrival of the next event, if it's modeled by an exponential distribution, which is the case of the Poisson process, that has no memory. So for this exponential distribution, which is typically in a catalog given with a parameter lambda called a rate, what is 1 over lambda, which is the mean of this exponential distribution? I close the poll in a second. Dirac on scale parameter, which is the correct answer. One way to see it, perhaps not the simplest way, but perhaps the most intuitive one. We've seen that sampling an exponential distribution can be done by doing 1 over lambda, an exponential distribution with rate 1 here, which means that, in fact, one way to produce a sample is to use this one and simply change the scale. We can also look at the PDF or the CDF, and we will see similar things here. So even though they may look very different when we plot them here, they're all different. All the exponential distributions are the same as the exponential one. They're simply a change of x-axis, of y-axis, which can be interpreted also a change of time units. Another question, a small quiz on agility in PDFs, probability 101. If capital F and capital G, those are CDFs, have the same shape, and the first, capital F, has a certain PDF little f, what can we say about the PDF of G, of the second distribution? Close the poll in a few seconds. And we have a tie for the first two answers, but the correct answer is the second B. G also has a PDF, but is not given by the formula A. There is a small additional term we need to add there. Whether a distribution has a PDF or not has to do with things like Dirac. We've seen that a random variable that is constant does not have a PDF, at least stricto sensu, doesn't have a function of which we can use it, by which we can express the CDF as the integral of this function, for example. Let's see why. It's useful to perhaps look at the details if you're not too familiar with those types of calculation. It is basic stuff in probabilities, but often gets forgotten because we tend to only use software packages. But rescaling, those are things that are important. So it's important to be able to do a change of variable when we change from log to natural scale. We need to understand what happens to our PDFs when you do that. So I do it in detail because it's important as a user of probabilities to do those kind of things, not things that software packages will do for us. So the topic here is what happens when I have a random variable x that is modified into a random variable y. So depending on your background and probability, you can use method 1. Method 1 is probably one that is taught in all probability courses that says that if I have a random here vector x that has a PDF little fx, then we transform it into y with a mapping h. Of course, the mapping, the transformation, to have a simple formula, we require that it's 1-to-1. That means we, for example, if h of x is x squared, which is not 1-to-1, then this mapping will not be so, the result is a bit more complicated with this method here. So here we really have to isolate a set where this mapping is 1-to-1, which is here the case for us. There's no problem because S is non-zero. This is a 1-to-1 mapping. Then there is this formula of transformation, how it gets a PDF transformed into the other one. And the way I remember this formula is to say that it gives the old as a function of the new. So we transform x old into y new with this formula. And this formula gives the reverse. It says that the PDF of the old function, of the old random vector, is obtained by this formula where h prime here is a Jacobian matrix evaluated at x of the transformation x to y here. And we take the determinant and the absolute value, and we apply it to the PDF of y, at least assuming both has a PDF. But if h is a function that has continuous derivative, if one has a PDF, then the other also has, if h is 1-to-1. And if the, at least in this direction. In our case, we have a much simpler case. We're in dimension 1, so that translates to this. The determinant is simply the derivative. So we take the absolute value of the derivative. Here our mapping is this one, Sx plus m. The derivative is s, so we obtain this formula. F of x, the PDF of the old variable, is s times the PDF of the new variable. Now, if I equate Sx plus m, the argument here, to little y, that gives me this formula, which means that the g of y is equal to this, or if I change the dummy variable y by x, that gives this formula. So there was a 1/s term that was missing, which corresponds to this determinant here, which justifies the answer B. I'm showing here an alternative method that is of independent interest because we will use it in the next module. And this is the method that I would say probabilists use. And that's a method that is perhaps more abstract, but is from a computational viewpoint simpler. Here, the method consists in observing that a PDF is a function f that has the following property. For any test function of the variable, random variable x, the expectation of f of x is the integral of phi of x, f of x dx. This is a theorem, sometimes presented as a theorem in a probability course, but that's perhaps the most useful way to think of a PDF. It's most useful because if f is a Dirac thing, then the integral of this can still make sense, as opposed to derivatives that are more often used here. So that's a property, but it's more than a property, it's a definition, in the sense that if this is true for a large class of function, then it entirely defines the PDF. For example, if I apply this to the indicator function of an interval, for example, of the interval -infinity c, here that will give me the CDF. So applying this function to all the indicators function of this specific form gives us the CDF. So if it's true for all those indicator functions, then it defines the CDF. The CDF entirely defines the probability distribution. So that is sufficient to justify that f is a PDF here. So that's my starting point that I will use in two ways. I will use it first as a starting point, but as an end point also, because if I am able to write expectation of phi of y in this form, which is what I obtain at the end here, then necessarily all the thing that is here is the PDF here. That's the trick here. So, but before anticipating, let me explain how I do it. So I want to find the PDF of y, so I take an arbitrary test function phi, I compute expectation of phi of y. Since y is Sx plus m, I apply the previous formula, but to the random variable x, and to the function which is not phi, but which is phi of Sx plus m. So that gives me this formula. Now I want the PDF of phi, so I need to have phi of something. So I must take this as integration variable. So I do a change of variable. I call y this quantity here, and I change the variable in the integral. Here I obtain dy is s dx. Because the derivative is positive, the order of the bounds remain the same. So I obtain expectation of phi of y is this integral here. And bingo, that automatically means that this thing is the PDF here. So if you know how to change variables in integrals, you can forget the previous formula. A third method, that is the one often taught in electrical engineering or computer science classes, we know that we define the PDF as the derivative of the CDF. Now I have this relation between the CDF. If I take the derivative, and if I don't want to embarrass myself with existence of derivatives, I take the derivative, and because of the 1s term, when I take the derivative, there's a 1/s that comes here, which is also another simple way to do it. Voila, 3 methods to solve the same example. I think you should feel comfortable with the 3 methods. You should be able to use any of the 3, and that's a good test to see how flexible you are in manipulating the basic constructions that are at the heart of statistics. Take-home message from what we saw a few minutes ago. In a good catalog of distributions, only distributions with different shapes should be mentioned. So for every shape, what we call a standard distribution is a particular one. Obviously, sometimes there is an obvious choice. For example, the standard normal, as we discussed before, is well known. The standard exponential is the exponential with rate 1. The standard uniform is the uniform returned by the random number generator, which is between 0 and 1. Any other uniform distribution on an interval is simply a change of both scale and location. So that's the first thing that will simplify our analysis of distribution. Remember, the problem I have is I have a data set. I have seen it. Perhaps I've plotted empirical PDFs, empirical CDFs. Perhaps I've done other things, that's what we'll see. And I would like to fit it with a certain distribution. For example, I would like to say whether this data is Gaussian. That's something we've often done. But we will see that in the context of modeling data sets in data science or in computer networks, that is not sufficient. So we use a catalog of different distributions. What we'll see now is what are the most often used distribution in this catalog. The log normal distribution is one of them. We've encountered it already, in fact, because in some of the plots I showed, I said, well, it doesn't look Gaussian, so let me take the log and it looks better. When I did that, in fact, I was using a log normal distribution. I was saying that my data had a log normal distribution. So a log normal distribution, X has a log normal distribution if log X is normal, which means X is exponential of Z, where Z is normal. Of course, that means X is a positive random variable because it's the exponential of a real number. And that is, as I mentioned, what we often find when we do some rescaling. So that's for a positive, the support, it's a positive random variable. Support is 0 plus infinity. Then we know that any normal distribution has the same shape as the standard normal distribution and can be obtained by this change of scale and location here, which means that exponential z, which is my x, is equal to this exponential mu times exponential z0 to the power sigma here. That's another way of seeing a log normal distribution. Here I'm plotting for various values of sigma and the same value of mu equal to 0, I believe. I'm plotting various PDFs of the log normal distribution. So you see that when sigma has this value here, which is large but not too large, it's almost like an exponential random variable. When sigma is small but not too small, it's almost like a Gaussian distribution here. Which leads us to this question. For the log normal distribution, which parameters is a location scale or a shape parameter? So here is a quiz that I invite you to address. I close the poll in a few seconds. Closing. Majority says A and B, but none of this is correct. In fact, I had given you a hint here. I'm showing 6 different log normal distributions with different sigma. And we see at least the first and the last have different shapes. The first one looks Gaussian, the last one looks exponential, which are not the same shape. And we see that there's a continuum from the first to the last. The shape changes, it becomes more skewed. It looks symmetric at the beginning, and it's very asymmetric at the end. Why is it so? Well, if I call X the log normal, the generic log normal, compared to this log normal that corresponds to the standard Gaussian, then we have that X is exponential mu times Y to the power sigma, right? So that means that if I change mu, I'm multiplying X by a fixed quantity, which is exactly a scale parameter. So mu, or in fact exponential mu, is a scale parameter. So for a log normal distribution, mu is simply changing the scale. So we can ignore it if we're interested in the shape. But sigma, as we have seen from the previous diagram, but which is perhaps hinted at by this formula, comes as an exponent. So if I take y, I put it to the power sigma, in general, by putting something to a power, changes the shape of what we're doing, which is what really happens here. So every different value of sigma gives a different shape. And I've illustrated that a few seconds ago, which means that there are as many different log normal distributions as there are values of sigmas here. So there is not one standard log normal distribution. This one does not qualify as the standard log normal, but the standard log normal distributions are all the log normal 0 sigma. That's what this discussion of shape means here. So that's important to realize. When I say my data is certainly Gaussian or my data is certainly log normal, I'm doing two very different statements. In the first case, I'm making a very strong statement because I'm saying the PDF always is the same modulo change of scale and location. In the second case, I'm saying something very vague because there are so many different shapes inside the log normal family that probably one of them can fit. To go further, statisticians use two indices called the skewness and kurtosis index to quantify some aspects of the shape of a distribution here. So the skewness is related to the third moment. So if I interpret my distribution, instead of writing integrals, I use the language of random variables. So if I interpret the distribution as the CDF of a random variable x, the first moment is the expectation of x. The second moment, which is called the variance, is the expectation of x squared minus the mean to the square, which is also the expectation of x minus the mean to the square. The third moment is the expectation of x minus the mean to the power 3. And the fourth moment, for reasons that we can discuss later, is given by the formula, is the expectation of the power 4 of x minus the mean minus 3 times the variance, which is the second moment here. Why we use that? Well, it has to do with the moment generating function of the variable, of the random variable. Those are, in fact, the first 4 coefficients of the moment generating function, which, if you remember, perhaps, is the Fourier transform of the PDF of the distribution. Why are we interested in that? Well, the first moment is the mean, the second is the variance, so those are location and scale. The third moment can be used to quantify how non-symmetric the distribution is, because if the distribution is symmetric around the mean, like the Gaussian distribution is, for example, then it's easy to see that the integral of this, if we break the integral into 2 parts, the part that's above the mean, the part that's below the mean, then by change of variable, we see that those 2 parts should have the same contribution with the opposite signs. So this third moment will be 0 here. So the measure that we use for this is, of course, this third moment, if it's non-zero, it's in the cube of the units in which we measure the random variable. So we rescale it by the scale parameter, which is the square root of the second moment. So it gives us this formula. The skewness index is the third moment rescaled by the standard deviation to the power 3, because it's a power 3 of the random variable here. So that is used as a measure of the asymmetry. It's negative when the shape is slanted to the right, and it's positive when it's slanted to the left. For example, for the random variables, we've seen before. No, I'm not giving the skewness, sorry. Another index of degree 4, the kurtosis index, is used to measure the departure from the Gaussian distribution. Why is that? Well, because in fact, for a Gaussian distribution, the skewness is 0 because it's very nicely symmetric around its mean. But also, the fourth moment is 0. This is because the Fourier transform of the PDF of the Gaussian distribution will give us exponential minus x squared plus modulo some rescaling numbers. So which means all numbers, all coefficients larger than 2 are 0 here. So this is one way to measure the departure from the normal distribution here, which is what was plotted on the series of diagrams here. This is the second index here. When it's 0, that means that for a Gaussian distribution 0, of course, it's not necessary but not sufficient. But it's interpreted by saying if it's small, it's not far from Gaussian. So I said, visually, this looks Gaussian. I was cheating a bit. In fact, the index is very small. We see that when it's far away from a Gaussian shape, the index becomes very large here. So this is a quantitative measure of how far we are from the Gaussian distribution. Now, if two distributions have the same shape, can we conclude anything about their skewness and kurtosis? I close the poll in a few seconds. And the correct answer is both. If you're not too sure, here is a formal proof. Well, I have a random variable capital X and one that differs by location and scale parameters. Then for the first moment, we will have this quantity, but the variances will be, the first moment will disappear from the variance and from all the other moments because we remove the first moment. So we'll have this relationship that the variance is multiplied when we go to y by s squared. When we go to the third kappa 3, the third coefficient of the generating function is multiplied by s cubed, s4 for the fourth one. And since the skewness indices are rescaled here, we find that they are the same here. Not surprisingly. So changing the mean, changing the location changes the mean, and since we remove the mean everywhere, that doesn't affect. And since we rescale by the scale parameter, obviously that gives the same thing. So the take-home message is that skewness and kurtosis indices are indicators of the shape of the distribution here. So that's one of the things that can be estimated to test whether we would like to take a particular distribution. For example, we might talk about the tests of the whether a distribution is Gaussian. We can test whether the skewness is equal to 0 and the kurtosis is also equal to 0 by estimating this third and fourth moments. This leads to the so-called Jarque-Berra test. In a catalog of distributions, typically you will find the values of skewness and kurtosis. Here's yet another distribution that's very often used in the context of data science, is the beta distribution. It's useful because it appears naturally when we do Bayesian estimation. So we see that's a family of distribution that has more parameters than it seems, because many depend on the shape. And here this, for example, a little textbook on distribution will give the skewness and the kurtosis. You see the skewness negative means it's slanted to the right, as I mentioned. The skewness equal to 0 means it's slightly symmetric. If you look at this curve, it's more bumpy than a bell shape. It's not degrading smoothly to the end, so it has a negative kurtosis. This one is thinner than a bell shape, so it has a positive kurtosis. So that's one of the aspects that are classically used to decide which distribution we would like to test to fit to our data. I mentioned the Jarque-Berra test. So that's yet another mechanism to test whether a distribution is normal by looking at the third and fourth moment of the distribution. The Jarque-Berra test is very useful in the sense it's really truly testing, not like the simple goodness of fit test is not estimating the distribution, but it has a drawback that we need to estimate the fourth and third moment. Now, perhaps you can easily imagine a drawback of using that. If there's one or two outliers in my distribution, then those moments will be very large and it will certainly say, no, it's not Gaussian. Perhaps it's just due to one or two outliers, which the Kolmogorov-Smirnov test, which is based on the CDF, will probably not react in the same way. I applied the Jarque-Berra test to the data that we had before, and we found different p-values, but the qualitative outcome is the same. The first plot is declared non-Gaussian, and the second plot is declared Gaussian. Voilà, so we've seen the log-normal family of distribution. We've seen the kurtosis and skewness indices. In the context of very large data sets, there is a feature that is often found, which is called power laws. That leads to a concept like the Zipf's law, Pareto distribution, that we will now discuss. Those are things that are very, very often found in large data sets, so we must be familiar with them to provide correct modeling. This is relatively recent because very large data sets are relatively recent. As long as statisticians used small data sets, they tended to find Gaussian distribution, and if it was not Gaussian, they would say, well, it's exponential. That was the most complicated we could get. But now that we have large data sets, we find that we need more things. So the first thing is called Zipf's law. That's an empirical law that was found in, for example, movies on Netflix or popularities of posted things on Facebook. If we rank the popularity of objects or posts in a certain catalog, most of the time we don't find a uniform or a Gaussian or even exponential distribution, but we find that the popularity of the jth most popular object is usually proportional to 1 over a power of its rank. So if you are number 100 in a catalog in terms of popularity, then your popularity, which means the proportion of users that will choose you, is some coefficient multiplied by 1 over your j to the power some index, which is not always the same, but has been consistently found that we find that type of relationship here. Which leads to, so that's a law which we can, empirical observation about popularity, which can be interpreted as a distribution, zeta distribution being the most common one, zeta or Zipfian. Zipfian comes from Zipf. The difference is that the zeta distribution is for an infinite set of values. So the zeta distribution says that I have to choose one object, one integer. So I will need to choose an integer j, which is the label coming from the rank of a given object. The probability that this object is selected is given by this theta j is 1 over j p plus 1. Of course, we need p larger than 0 because the infinite sum of all the j must be summable. But the sum of all those infinite numbers of j to the power p plus 1 must be finite, and eta is the normalizing constant, is 1 over this infinite sum, so that we have a probability. So this is called the zeta distribution. It's a distribution over integers that has this power law. Its PDF, the probability that integer j is taken, is 1 over j to the power p plus 1, or to the power some integer. If we do the same thing, but in a catalog, in a finite catalog of n objects, it's similar, but it's called a Zipfian distribution. Here, since n is finite, we don't need to require that the exponent is large enough so that the power series converges. But that's the only difference. In practice, most often people equate the two because n is large here. Why do we care about that? Well, because it has been found quantitatively, but also because its tractable version, which is the Pareto distribution, is very often used as it explains many phenomena that are found. So Pareto is the same, but assuming the variable x that we draw is a real number, not an integer number, a real larger than 1. So the Pareto distribution has support on the set of numbers larger than or equal to 1. And its PDF, the probability of choosing something close to x, is given by 1 over x to the power p plus 1 times a normalizing constant. And this normalizing constant is just p. So it's the continuous approximation of zeta and zip. But here, the math is straightforward. For example, computing the normalizing constant is easy. It's just p, because the integral from 1 to infinity of 1 over xp plus 1 dx gives exactly 1 over p. The standard Pareto is exactly, so what we said here is the standard Pareto. So this PDF that I've explained here is standard because we start at 1. Now, if I want to rescale, I will start at something else. And its complementary CDF is 1 over x to the power p. Complementary CDF means 1 minus the CDF. The CDF is the probability that a sample is larger than something. The complementary CDF is the probability that is less than or equal to something. That's the textbook definition of CDF. Pareto is often used when we have tails of distribution that are of interest because we have large rare events. So we're interested most often into the probability that x is larger than x, which happens here to have a very simple formula. It's given by 1 over x to the power p. And in fact, both the PDF and the CCDF follow a power law. Power law is the name that physicists give to an equation of the type y is equal to ax to the power b, which in log scale gives a linear relationship. So if we take the log of the argument and the log of the PDF or the log of the CCDF, very often for large data sets, we find that they appear to be on a straight line. This is a phenomenon called the power law. And this is not consistent, of course, with Gaussian or exponential distributions here. I've mentioned the standard distribution with index, Pareto distribution with index p. What can we say about p? Is it a location or a scale parameter? I close the poll in a few seconds. And the majority says that P is a location parameter, but this is not correct. In fact, it's not a location parameter because all of these distributions have the same support. So if it would be a location parameter, then I would need to move this interval. It's also not a scale parameter because if I have different indices P's, a power of P cannot be just a change of scale equal to another exponent here, because you do just a ratio that cannot be a constant. Therefore, P is a shape parameter. So there is one Pareto distribution per P. In fact, I call it the standard Pareto, that one that starts at 1. If I shift it and rescale it, I will have all the variants of it that have the same shape. But if I change P is called the index or the parameter of the Pareto distribution, I change the shape. And we will see that this has a radical importance. We'll see that indeed, different Pareto distributions lead to different qualitative properties when we go to aggregation and computation of confidence intervals, for example. But before getting there, here is a plot of 3 distributions in log-log scale. When I say distributions, it's in fact the CCDF, complementary CDF. A CDF is a function that goes from 0 to 1 and is increasing. And most of the time, all CDFs look very similar. So it's very hard to see the shape of a distribution by looking at its CDF. The PDF is more informative, and the complementary CDF is also more informative. The complementary CDF, of course, decreases and goes to 0 as x goes to infinity, because the probability that the random variable is larger than a value on the x-axis. And here the x and y-axis are in log scale. So of course we see that they all decay to 0, but with different properties. One of these distributions is a normal distribution. Another one is a log normal distribution with some shape parameters, some sigma. And another one is a Pareto distribution with some shape parameters, some p. Which one is which one here? Whoops. So I'm giving A, B, C as names to those different plots. For example, if you choose answer A, that means you think A is log normal, B is Pareto, and C is normal. Make your choice. I close the poll in a few seconds. Closing. And the majority makes the second choice, which is the correct one. Why is that? Well, first we saw that Pareto has a power law for its CCDF. So we should see a straight line in log scale. So A must be Pareto. Now we have C and B. Now, remember that log normal is a misnomer. In fact, log normal means the exponential of a normal. So it's something that's more variable than a normal distribution. And we found instances, for example, where we saw we had a data set with a few very large values. So we took the log of it. So that means this data set that has a few very large values that are not consistent with a normal distribution, we model them as log normal. So log normal has a heavier tail. The probability that we see a large value is less. So that says that B is the log normal and C should be the normal distribution here, which is the correct, which gives the answer B. Voilà, so the Pareto distribution has to do with the power law. If you do the CCDF plot of your data, you see a straight line, at least on a large fraction of your data, probably fitting Pareto, or at least fitting the tail with Pareto would be a good idea. Yet another important feature is the hazard rate. The hazard rate is also related to the tail of the distribution. The tail of the distribution is important because this is what tells you whether large values are anomalies, they are outliers, or they are parts of the system. And it's important to model them because, at least depending on the system, a few very large values may radically modify the performance of your system. The hazard rate is given by this definition. It's a function. So I have a PDF or a random variable capital X on which I'm able to evaluate probabilities. Lambda of X is given by this formula. It's the limit when dx goes to 0, the probability that x is less than x plus dx, given that x is larger than x. So it's a conditional distribution. Right? So it means we can interpret that by saying the probability, if I interpret capital X as the lifetime of an object that will die, the probability that the death of the object occurs now, given that it's alive now, is proportional to lambda x dx here. So that's why it's called a hazard rate. It's the rate. That's the rate at which things will die, given that they are as old as that. So that's a quantity that's used, of course, for life insurances in populations. And if we have the distribution of ages in the human population, of course, this rate increases and tends to become very large, goes to infinity, when the value of x increases. The older you are, the more likely you are to die. That's for all living beings and even for artificial constructions here. But we have distributions that are memoryless. For example, we talked about the memoryless property of the exponential distribution. And this property means that this rate tends to be constant. Given that I have observed that this light bulb has been working for 2 years, it doesn't tell me any information about whether it will die in the next minute or not. If this rate C is, so C times a minute is the probability that the light bulb will die in the next minute. If it's constant, it means it's a memoryless property. Of course, most systems are not memoryless, but we have distributions that have the memoryless property, and up to some time scale, they are useful. For example, the time you need to wait until a disintegration of an atom takes place is modeled by such a memoryless property. And something even more counterintuitive is the fat tail, also called vanishing hazard rate, is when it goes to 0. So that means that given that some object managed to live long, it is very likely that it will live much longer. So that probably does not exist in all rigor for x going to infinity, but it can exist within a given time scale when I have competition systems, for example, and if an object or a phenomenon is in competition with other phenomenons, the fact that you could observe it after several hours here means that's the winning one. That's the one who will survive. And given this one will survive, it will live very long here. So those are 3 very different qualitative behaviors of distributions that can be estimated because those are conditional probabilities. For example, if you have a large number of experiments, you can quantize your lifetime, and at every time in your simulation or your measurement experiment, you can count all the objects that have lived so far, see how many of them will die in the next minute or died in the past minute, and this ratio will give you the function lambda of x, which you can then index by x. So if you have large data sets, that's a feature you can quantify. We have seen three families of distribution: exponential, which is in reality one distribution, all have the same shape; Pareto, which is a family of distribution, and the normal. And what statement is correct? Is it true that exponential is aging, that Pareto is memoryless, and that normal is fat tail, or some other combination? I close the poll in a few seconds. Closing now. We find a very even distribution of answers. The correct answer is the last one. Let us see why. Well, the crux is to find, in fact, this formula. Where does this formula come from? Well, by the definition of conditional probabilities, we can interpret that by saying, well, the probability that X will not survive this, given that X is larger than now, is the same as this, because given this, that's a trick we've often used when we talk forecasting, when we do a conditioning, that means we assume the event that is there happens, it's certain, it's not a random thing. So we know that capital X is less than X. So saying that it's less than X plus dx is saying this here. And now, what is this? The probability, I'm doing a heuristic argument. The probability of an event given another one is the probability of the end of the event divided by the probability of this. So what is the probability of the end? Is the probability that capital X is in this interval and X is larger than X. Well, this end is useless because this and that is equal to that. So it's the probability of this divided by the probability of that. The probability of this, one physics style interpretation is, this is the PDF multiplied by dx. In fact, this is the interpretation of the PDF. This is how we do empirical PDFs. We take a small quantization step dx and we count how many outcomes are in an interval with length dx. This is how we do what is called a histogram, which is an approximation of the PDF. So a theoretical interpretation of the PDF is that the probability of this event is the PDF f of x multiplied by dx plus terms that are the terms, but they are little o of dx. They are negligible when we divide them by dx. They go to zero when we divide them by dx. So this is equal to f of x dx divided by the probability of that. The probability of that, that's what we've seen in the CCDF. It's 1 minus the CDF here. Since we divide by dx to obtain the rate here, we obtain this other equivalent formula. The hazard rate is simply a combination of the PDF and the CDF, is the ratio of the PDF, and the CCDF is the ratio of the two. So this ratio is therefore the crux to understand the answer to my question. Now for the exponential random variable, we know the PDF, it's exponential minus lambda x times a normalizing constant, which is lambda. 1 minus the PDF, so the CCDF is exponential minus lambda x, By the way, that's a nice way of thinking, of remembering the exponential distribution. Its CCDF is simply a negative exponential. And for the standard exponential distribution, we have lambda equal 1. So the simplest negative exponential gives us the CDF of the exponential. Now, if I do the ratio, this divided by that gives me lambda. So for an exponential random variable, the hazard rate is just the rate of the exponential distribution, which is consistent with the interpretation of the exponential distribution. First, it's memoryless. It's the same always, which means there is no memory, in the sense that whether you have lived long or not doesn't change your lambda. Lambda remains the same. We don't remember how much time you spent. And we have seen this already when we talk about the Poisson process used for modeling arrivals of events, for example. We see that we model the inter-arrival of events as an exponential random variable, which is exactly saying this memoryless property. So this is things we knew already, at least in theory. For the Pareto distribution, we can do the same thing. So one way also that is very simple to think about the Pareto distribution is that its CCDF is 1 over x to the power p for the standard Pareto. Standard is the one that starts at 1 here, and its PDF is a more complicated. Now, if I do the ratio, this divided by that, I will find P over X here. P over X means this is an example of what we call the fat tail. This is this counterintuitive thing. Given that something is large, it's likely to be very large. That's another way to think about it. Given that some quantity has lived, some object has lived long enough, X is large. Given that you've observed that this object is still alive now, the probability that it will die now becomes smaller and smaller. That's a property, a counterintuitive property of the Pareto distribution, but that is one that has been found in large data sets. So people have found some explanatory models for that, how those objects emerge. They emerge typically by the result of competition, and the intuition is perhaps the one I gave a few minutes ago. The thing that you see that is large, it is large. You see it now because it has survived some competition. For example, in YouTube, your video is watched a lot because it managed to escape the fate of all the YouTube videos, like my lectures, that are not seen by a huge number of people. But once you survive this competition that lets you being propagated, then you will be watched by a large number of people. So given that you're large, you're likely to be very large. It's a paradoxical thing that we see in artificial constructions in the world of information technologies, but also, for example, in nature. There has been to illustrate what happens with the climate. The occurrence of floods, for example, uses that kind of models here. So Pareto is fat tails, which is one of its very important property, and has to do with the power law. Now, the normal distribution, well, we expect that it's aging, right? Because a normally distributed lifetime means you live for so much with a small variance about it. But if you've lived much, much larger than the mean plus 2 or 3 sigma, you're very likely to be dead very soon, which is unfortunately what happens to us humans. Now, mathematically, we know the PDF is a constant times roughly exponential minus x squared. And the CCDF doesn't have a closed form, but in equivalent term, it can be shown that it is, if we ignore some terms here, it's in 1 over x times exponential minus x squared over 2. So that the rate is in x, so it goes to infinity as expected here. When aging is an important parameter in a distribution, then we're confronted with a issue of finding a distribution that fits a given age parameter. And for this, typically, we use the Weibull distribution. What is the Weibull distribution? Well, the standard Weibull distribution has CCDF, which is exponential, negative exponential, of a power. So there is an exponent in the power. So for c equal 1, we find, of course, the exponential distribution. So for c equal 1, we have the good old exponential distribution, which is memoryless. And for c larger than 1, it is aging. which we see here, it starts looking like a Gaussian distribution. We see that its kurtosis index becomes very small, so it means it is close to a Gaussian distribution. And when C is small, then it is fat tail. It starts looking like to be put in the same box as the Pareto distribution. Here, it's a large departure from Gaussian, as we see from the kurtosis index. So if you want to fit a given aging parameter for your data set, then many people will use Weibull distribution because it gives you the flexibility. Voilà, thank you for the 1 minute of overflow today. We stop here for today. Tomorrow we will continue and finish this module, and we will discuss the fascinating implications of the power law and the results, the counterintuitive results that come out of that. I wish you a good continuation of the lab, and as usual, we stay online to address your questions. Take care.